Okay, shall we start? Today is going to be the last discussion for the semester, and we're going to do um, some problems from chapter 7 and 9. So, first, prove that every uniformly convergent sequence of bounded functions is uniformly bounded. Okay, first, what do we mean by uniformly bounded? So we all know what it means for a function to be bounded, right? Say f of x is less than or equal to m. Um, so that's bounded, right? It doesn't matter what x is, but f is always bounded by this number. So uniformly bounded means that, so here we have a sequence, right? So f1, f2, f3. All the way to Fn and so on and so on. So uniformly bounded means there is a constant that bounds each of those functions. So that means Fn of x is less than, say, m for all n x. Okay, so how do we prove that? So first, what do we know? So we have so let us know the sequence Fn, right? N from 1 to infinity. So it's uniformly convergent sequence of bounded function. So each of those Fn is bounded by some constant, but potentially depends on n, right? So let's say they are all less than or equal to mn. Okay. So now because our sequence is uniformly convergent, so for any x, right, for any x, there exists a n, right? So such that for all n and m greater than n, fnx minus fmx is less than, say, 1. Okay, so that is just saying for any particular x, this sequence fnx is a Cauchy sequence, right? So here I just picked epsilon to be 1. Of course, you can pick epsilon to be anything as long as it's not infinity. Okay. All right. So then fmx is less than or equal to say fnx plus fmx minus fnx, right? This is triangle inequality. So the idea here, right? So this mn potentially depends on n. So we want to get rid of this subscript n. Okay, so first we have this inequality. Now we know this is bounded by m sub n plus 1, right? Because this is bounded by 1. So this bounded by this bounded by this. So fmx is bounded by this. Okay. So then if we take m to be the maximum of m1, m2 all the way to mn, then this is less than or equal to m plus 1. Okay, so that's how we get rid of the subscript, because here we picked 1, right, as our epsilon. So this big N is fixed, so it makes sense to take the maximum of that the maximum of finitely many numbers is finite, so m is a finite fixed number. So finally we have this is less than or equal to that, and this is independent of m and x. Okay, so that shows the sequence is uniformly bounded. Okay, so next, if fn and gn converges uniformly on the set E, prove that their sum also converges uniformly on E. And if in addition Fn and Gn are bounded sequence of bounded functions, prove that Fn, Gn, the product, converges uniformly on E. Okay, so how do we do that? So first, let's look at the sum. So our goal is to show, right, Fn plus Gn of x minus, say, Fgx goes to 0, right? Where so what is f? So f is the limit. So f of x is the limit of fn of x, right? And g of x is the limit of gn of x. So intuitively, fn plus gn converges to f plus g, right? So let's prove that. Okay. So how do we do that? Well, the idea is pretty simple. How do we show these two are close? Well, you show, okay, fn is close to f and gn is close to g. So the sum has to be pretty close. So what you can do is you can rearrange them, right? You have fn minus f. And then plus gn minus g. Right? This is less than or equal to because of the triangle inequality. So because f converges uniformly, so this goes to 0, right? And this goes to 0, so that goes to 0. Okay, so that proves the first part. Now for the second part, so how do we do that? So again, same idea. Intuitively speaking, fn gn of x should go to f times g of x, right? So we want to show that goes to 0. So here's what we're going to do. Because f and gn are both bounded functions, right, and converges uniformly. So by the previous problem, we know that the limit or the sequence is uniformly bounded, right? So there exists an m such that fn of x is less than m and gn of x is less than m for all n and x. Okay? Because of uniform convergence, then we know that both f and g are less than a bounded function by m. Okay, so all right, so we're gonna okay, so here's what we're gonna do. So we can choose n1 and 2 such that fn x minus f of x is less than, say, epsilon over 2m, and gn x minus g of x is less than epsilon over 2m. So this is for all n greater than n1. That's for all n greater than n2. Okay? And then, so we want to show this goes to 0, right? So here's what we're going to do. Okay, so maybe let me erase this. So we want to show fn gn minus fg goes to 0, right? So here's one trick that we usually do. So we want to bridge in between, right? So fn gn, we first take a limit of f, so f gn, and then we add it back, right? And then we use triangle inequality. Okay, now this we can factor out a gn, right? fn minus f, and that we can factor out an f. So gn is bounded by m, and that we can choose m big enough, right? So that's less than epsilon over 2m, and this is less than m, that's again less than epsilon over 2m, and then, right, everything cancels, that's less than epsilon, so that shows it goes to 0. Okay, so next, construct sequences fn, gn, which converge uniformly on some set E, but product does not converge uniformly on E. Okay, first of all, they have to converge, right? But the issue is uniform convergence. Okay. So can we think of such an example? So here's a simple example. We take the sequence fn to be the identity function. So it's always equal to x, right? So this is a sequence of functions, but each function is the identity function. And gn of x, we can take it to be the constant function, say 1 over n. Then obviously fn, that goes to x, right? Because it doesn't change, and gn goes to 0. Okay, and the convergence uniform, right? It's obvious because it doesn't even change, and that a constant function converges to 0. That also uniformly convergent. Okay, but fn of x times gn of x, does that converge uniformly? Well, first of all, it converges to the 0 function, right? Because it doesn't matter what your x is. If you let n go to infinity, for any fixed x, that goes to 0. But is the convergence uniform? No, it's not uniform. Why? Because it doesn't matter what your n is. You can take your x to be n, right? So if x is greater than n, then your function does not go to 0, right? So so you can see that the convergence is uniform because, right? Because if you look at this function, there exists an x, namely x greater than n, such that x over n does not go to 0. It's not equal to 0, right? In fact, x over n is greater than 1. So xn minus the limit 0 is greater than 1, right? That does not go to 0. Okay, next problem. So let fn of x be 0 when x is less than 1 over n plus 1 and equal to sine square pi over x when x is between 1 over n plus 1 and 1 over n, and it's 0 if 1 over n is less than x. Okay, so first show that fn converges to a continuous function but not uniformly. Okay, and then use the series to show that absolute convergence even for all x does not imply uniform convergence. Okay, so how do we do that? Well, so first we show fn converges to a continuous function. So first of all, what's the limit of this function? So limit fn of x as n goes to infinity, that actually converges to the 0 function. And why is that? Because, say, this is 1 over n plus 1, and this is 1 over n, right? So to the left of 1 over n plus 1 is 0, and to the right of 1 over n it's also 0. So something can happen between 1 over n plus 1 and 1 over n, right? But as n goes to infinity, this interval is getting smaller and smaller, right? Eventually shrinking to a point. So, so as you can see, it goes to 0, right? Because you pick any number on the real number, right? On the real number line, you can make you can make n big enough so that eventually 1 over n plus 1 and 1 over n, this interval, exclude that point. Okay. All right, so the convergence is not uniform. Okay, not uniform convergence. Why? Because we can take x to be 1 over 2n plus, say, 1 over 2. Then pi over x is equal to what? Is equal to 2n plus 1/2 times pi, right? So sine square of 2n plus 1 over 2 pi is the same as sine square of 1 over pi. And sine 1 over pi is equal to 1, right? And does not go to 0. So the convergence is not uniform. Okay. So next we have to look at the series. Okay. So this series converges to what? So first observe that um, so for different n, this 1 over n plus 1 and 1 over n are disjoint, right? Say n is equal to 1, it's 1 and 1 half. If n is equal to 2, that's 1 half and 1 over 3, right? If n is equal to 3, that's 1 over 3, 1 over 4, right? So, um, so these intervals are always disjoint, right? So it's not hard to see that the series converges to 0 when x is less than 0. Um, okay, and when x is between 1 and 0, it is sine square pi over x. Okay, and it's equal to 0 for x greater than 1. Okay, I don't know if it's easy to see. So let me erase these and write it again. Okay, so let's see. So say when n is equal to sorry, this should be n plus 1, right? So when n is equal to say 1, so we have so that's say 1 half, right? This is 0, this is 1. So less than 1 half, it's 0, and greater than 1, it's 0, and you have something, right, here. So when n is equal to 2, we have it's 0, it's 1 over 3, 1 over 2. So greater than 1 over 2 is 0, and less than 1 over 3 is 0, and you have something here, right? Now, so when you add, say, f1x plus f2x, what do we have? We have less than 1 over 3, it's 0, right? Between 1 over 3 and 1, so you have something here and something here, right? So when you add another f3x, then you have here 1 over 4, right? Something here, and as you can see, if you keep adding more and more, you're adding things here, right? So eventually, your function converges to this. So 0 when x is less than or equal to 0, and 0 when x greater than or equal to 1, and it is sine square pi over x when x is between 1 and 0. Okay? So this convergence is absolute because, as you can see, each term is non-negative, right? So we know this sum, we know this converges to that, right? And each of those is non-negative, so put on absolute value, it's not going to change anything. Okay. So as you can see, your function is not continuous at 0. Because when x close to 0, this is in the denominator, right? So this thing changes really, really fast. So it's not continuous at 0, right? Okay. but we know the partial sum is convergent, obviously. So even though we have absolute convergence, but the limit's still not continuous. So that means that we don't have uniform convergence. Because if we have a uniform convergence, then uniform convergence continuous function is continuous, right? The limit is continuous. But here, as we can see, the limit is not continuous. Therefore, the convergence is not uniform. Next, prove that the series sum n from 1 to infinity minus 1 to the n x squared plus n over n squared converges uniformly in every bounded interval but does not converge absolutely for any value of x. Okay, so first, how do we show convergence is uniform in every bounded interval? So we can decompose this into sum of two series. Okay, so let's see. The first is convergent in every bounded interval, right? Because this is convergent, right? For any fixed x, this is bound by some number m, right? Okay, so the tail of the series is less than, say, n from 1 to, say, n from n to infinity. I can put on absolute value, right? M over n squared. So maybe I should say this. So this greater than that. And we know the tail of this series goes to 0, right? So that goes to 0. So this is convergent. And this is alternating series, right? And it's independent of x. So it converges uniformly in x. But it's not uniformly convergent. Why? Oh, sorry, it's not absolutely convergent. Why? Because this because if we take the absolute value, right? So this is greater than or equal to that, right? Because x squared is always positive, and after putting on the absolute value, this thing is gone, and we know this is divergent, right? So the series is not absolutely convergent for any x. Next problem, define f of x equals to e to the minus 1 over x squared for x not equal to 0 and is equal to 0 when x is equal to 0. So prove that f has derivative of all orders at x is equal to 0 and that the derivative at 0 is equal to 0 for all n. Okay, so let's do that. Okay, so what do we do? Well, so let's compute the derivative first when x is not equal to 0. Okay, so for x not equal to 0, first of all, it's easy to see that this function is continuous at 0, right? Because you can imagine if x is very small, then x squared is even smaller. So minus 1 over x squared goes to minus infinity, and e to the minus infinity is 0. Okay, so our function is continuous. Now let's compute the derivative. So to compute the derivative, we use the chain rule. Okay, so we have, let me rewrite this as e to the, okay, so e to the minus 1 over x squared derivative is equal to e to the minus 1 over x squared times the derivative of minus 1 over x squared, right? So minus 1 over x squared is minus x to the minus 2. So if you take derivative, that's equal to 2 to the x times 2 times x to the minus 3. Right, that's the first derivative. Now for the second derivative, we have to use the product rule, right? So we first differentiate this. So that's first derivative. The second derivative, if we use the product rule, what we're gonna get is we differentiate this first. So minus 6x to the minus 4 times e to the minus 1 over x squared, and then what? And then plus 4x to the minus 6 e to the minus 1 over x squared, right? And third derivative, and you can compute, then you further use product rule and chain rule, right? So in any case, you always have, so it's always a sum of some constant c times x to the minus, some k, right, times e to the minus 1 over x squared. It's always in this form, as you can easily see. So then here's a fact. So fact, fact is x to the minus k times e to the minus x squared goes to 0. Okay, so limit as x goes to 0, this is equal to 0. And you can show this by, say, L'Hopital's, okay, by doing L'Hopital many times. Okay, I'm gonna skip the details. So if you take limit as x goes to 0, right? So the limit of the derivative goes to 0. So in fact, it is the derivative is 0 at 0. Okay. All right. Okay, so here's interesting phenomena. So so first of all, our function is not equal to 0. It's not a 0 function, right? But since the derivative is all 0, so if you think of its Taylor expansion, it's gonna. So let's review what is Taylor expansion. So it's f. Taylor expansion is 0, right? It's f of 0 plus f prime at 0 over 1 factorial plus f double prime at 0 over 2 factorial, etc., etc. So f of 0 is equal to 0, right? And all derivative is equal to 0. So paradoxically, even though our function is not 0 and continuous at 0, but its Taylor expansion 0 does not equal to that function. Okay? All right. Next. Let Aij be the number in the ith row and jth column of the array. So minus 1, 0, 0, 0, and 1 over 2, minus 1, 0, 0, 1 over 4, 1 over 2, minus 1, 0, 0, and then 1 over 8, 1 over 4, 1 over 2, minus 1, okay, and so on, so on. So I'm pretty sure you can see the pattern. So the diagonal is always minus 1. So the upper triangular table is 0, and the lower triangular is what? 1 half, 1 over 4, 1 over 8. So it's 1 over 2 to the sum power, right? Okay, so in fact, we can write Aij equals to 0 when I is less than j, so it's the upper triangular part, and it's equal to minus 1 if I is equal to j, so that's the diagonal, and it's equal to 2 to the j minus I if I is greater than j. Okay, so prove that sum Aij, so we first sum the j index and then sum the I index. So this sum is equal to minus 2, but if we switch the order of summation, we sum I first and then j, we get 0. Okay, so let's do that. So for the first sum, so this is equal to sum I from 1 to infinity, right? So Aij, so we are summing over j, right? So okay, so that's, we have minus 1 when I is equal to j, right? And then j from 1 to I minus 1, right? We have 2 to the j minus I. Okay, and then if j is greater than I, okay, so that's how it goes. So we first look at when j is less than I, so that's when j from 1 to I minus 1. So Aij is equal to 2 to the j minus I, and then we hit j is equal to I, that's how we get the minus 1, and after that it is 0. Right, okay, so let's compute. So this is just the partial sum of a geometric sequence, right? So we all know the formula for this, so I'm just gonna write it. Okay, and then minus 1 and 1 cancels. Okay, so again, this is a geometric series, and we all know its sum, it's minus 2. Okay, so that part is proved. Now, for the second part, for the second part. Okay, so now we are changing I, right? So when I is less than j is equal to 0, right? When I is equal to j, it's minus 1. And when I is greater than j, so when I is from j plus 1 to infinity, we have um, 2 to the j minus I, right? So this, again, is a geometric series. Okay, so when I is equal to j plus 1, this is um, equal to what? When I is equal to j plus 1, this is 2 to the minus 1, right? When I is equal to j plus 2, that's 2 to the minus 2, right? So it just essentially um, the sum is just 1/2 plus 1 over 4 plus 1 over 8, right? So on and so on. And this geometric series, we all know the sum is equal to 1, right? So minus 1 and 1 cancels, give you 0. So you are just summing up a bunch of zeros. So you got 0. So the moral of this problem is that, as you can see, when we are dealing with infinite sums, you cannot simply switch the order of summation. Okay, but if your series is absolutely convergent, meaning that if you put the absolute value, then you can switch the order. Okay, so this is related to the Fubini theorem that you see in calculus, right? Recall, in calculus, we sometimes do the order of integration. We sometimes switch that, right? But this is not valid for all function. So when is this valid? When can you do that? And then you have to look up Fubini's theorem. So these two are no different because essentially a summation is an integral, right? Summation is like the discrete version of integral. So same phenomena will appear over here. Okay, next, prove the following limit relations. So we have limit as x goes to 0, b to the x minus 1 over x equals to log b for b greater than 0. Okay, so how do we prove that? Okay, so let's consider the function f of x equals b to the x. So another way to write b to the x. So first of all, when we look at that, it looks like a derivative, right? If we add a minus 0 there. So it looks like a derivative of some function when x is at 0, right? So naturally your function would be b to the x, and so just for comparison, I'm going to write it over here. So this is equal to the derivative of f at 0. Okay, so now if f of x is equal to b to the x, then f of 0 is equal to 1, right? So that's exactly that. So this really is the derivative of this function at 0. Okay, so to compute the derivative of this, we have to first convert it to some function that we are familiar with. So this can be written as, so b, you can write it as e to the log. So log and ln are the same thing, right? I'm just going to write log for ln. So this is equal to e to the x log b, right? So we all know how to compute this, right? So f prime of x is equal to, by the chain rule, log b times e to the x, right? And then we plug in x is equal to 0, we have this equal to log b. Okay, so that's that. And next, limit as x goes to 0, log 1 plus x over x equals to 1. Okay, again, okay, so okay, so what do we do with this? All right, so here's the trick. So if we let y equals to log 1 plus x, then x is equal to what? X is equal to e to the y minus 1, right? So really this is the same as, okay, so here we have x goes to 0, right? And as you can see, if x goes to 0, then y goes to log of 1, and log of 1 is equal to 0, right? So x goes to 0, the same as y goes to 0. So now this is y over e to the y minus 1, right? So that's what we want to show. Okay, so so what do we do? Well, so recall the last problem, we proved the following. Right? So this is equal to 1, and as you can see, this, so we're really computing the reciprocal of this when b is equal to e, right? So there's no surprise, the answer should be 1. Okay, but how do we do that? Well, we flip it, right? So it's equal to the limit y goes to 0, 1 over e to the y minus 1 over y, right? So because the limit of the numerator exists because it's constant, and the limit of the denominator also exists because of the previous problem, so we can write this as 1 over limit as y goes to 0, e to the y minus 1 over y. Right? Okay, so this is equal to 1, so that's 1. Right, this. Okay. All right. Next, limit as x goes to 0, 1 plus x to the 1 over x equals to e. Okay, so we know limit as x goes to 0, 1 plus, oh sorry, we know the following, right? But now you see this a little different. So it's 1 over x here, that it's x. That's x, that's 1 over x. But now we have x goes to 0 instead of x goes to infinity. Okay, anyways, so really there's no surprise that the limit is equal to e. But how do we prove that? Again, we have x in the base and in the exponent. So whenever you see something like that, a common trick is this. So you'll write this as e to the log 1 plus x over x. Okay, so that way you only see x in the exponent. All right, so then by previous problem, we know that limit as x goes to 0 log 1 plus x over x, this is equal to 1, right? So the exponent goes to 1, so if you take the limit, that goes to e. Okay. All right. So next, limit as n goes to infinity, 1 plus x over n to the power of n. Let's prove that the limit is equal to x. So again, same thing, right? So we see the okay, so how do we show that? Well, so here we have x over n, but here we just have n, right? Well, it would be nice if this is also the function of x over n, right? So let's recall we have this. So we know this is equal to e, right? It will be, so you will see this exponent is the reciprocal of this. So it will be nice if this can be the reciprocal of that. So what do we do? Well, this is equal to 1 plus x over n. So it's 1 over x over n, and then we raise it to the power of x, right? Then as you take limit, so remember here we are taking limit as n goes to infinity, right? So this x stays put. So if you take limit, the things inside, so this is equal to e, right? By that, you simply replace x by x over n, right? Okay. So so this is x goes to 0, right? X goes to 0, the same as n goes to infinity here. So we know this is e, so the base goes to e, so the whole thing goes to e to the x. Okay. All right. Next, we have a sequence of functions. Fn is equal to 0 if x is less than minus 1 over n, is equal to n times x plus 1 over n if x is between 0 and minus 1 over n. It's equal to n times minus x plus 1 over n if x is between 1 over n and 0, and is equal to 0 if x is greater than 1 over n. So we want to show that Fn is continuous, but the limit is not. Okay? All right. So let's see. So the function is continuous, obviously, on each of those intervals. So you only have to check that the function is continuous at the endpoints, right? So your function probably looks something like that. So you have to, so this part is fine, this part is fine, this part fine, this part fine. So you have to check those parts, right? So let's do that. So we have to check when x goes to minus 1 over n from the left, it's equal to 0, right? From the right, you just plug in x equal to minus 1 over n, then you have n times that, and that's equal to 0, right? So it's continuous here. So same story, x goes to 0 from the left, and x goes to 0 from the right, both equal to 1, right? And finally, uh, when x approaches 1 over n from the left, it's 0. From the right, it's also 1. Okay? Um, so that's that. Okay. All right. So why the limit is not? So say this is f1. If you draw the graph for f2, it looks like that. f3, it looks like that. So as you can see, it goes sharper and sharper at 0, right? Because as you can see, this is essentially a linear function that is at 0 when x equal to minus 1 over n, and is equal to 1 when x equal to 0. And the slope is n, right? So the slope is getting steeper and steeper, but at 0, the maximum of this function is always 1, right? So it looks like that. So eventually, it converges to this function. So it's 0 everywhere, but 1 at 0, right? So obviously, the limit, the function is not continuous because not continuous at 0. So again, as you can see, the convergence is not uniform, even though your function is all bounded, right? Because if you have uniform convergence, a bunch of continuous function will converge to a continuous function.